Hello everybody, welcome to UGC EPG Pathshala. Back again to GIS, and now you know what is GIS and you understand the nuances of GIS operation. Let's now talk about the strength, the basic strength of GIS today in the form of a lecture on overlay operations and analysis in GIS. I am Dr. Seema Mehra Parihar. I've been teaching remote sensing and GIS now for the last 30 years, and in addition I'm also teaching natural resource management. I've got my PhD from Delhi School of Economics, Department of Geography, got my share of learning of remote sensing GIS from IRS Dehradun, and I've got a postdoc fellowship at ITC Netherlands, where again I got exposed to these tools. Let's start our journey of learning overlay operations and analysis. Today what we are going to do is we are going to understand the concepts of spatial analysis in geospatial environment. We are going to be able to give a brief description of overlay analysis in GIS. We will be able to comprehend importance, uses and essential characteristics of these all analysis. We will also be able to visualize the role of vector and raster data model in these analysis. So let's start going. We all understand by now, definitely, that spatial analysis is the vital part of GIS. It can be done in two ways, one the vector-based and the other the raster-based analysis. Since the advent of GIS in, you can call it 80s, 60s, 90s, many government organizations have invested heavily in GIS installations, including the purchase of hardware and software and the construction of mammoth databases. The two fundamental functions of GIS have been widely realized. One is generation of maps. Second, generation of tabular reports. Both are important. And indeed, of course, GIS can provide a very effective tool for generating maps and statistical reports from a database. However, GIS functionality far exceeds the purposes of mapping and report compilation. Please keep this in mind. In addition to the basic functions related to automatic cartography and database management systems, the most important use of GIS are spatial analysis capabilities. Just remember SAC. Spatial analysis capabilities is something what GIS is all about. As spatial information is organized in a GIS, it should be able to answer complex questions regarding space. And this you know, which you've done in Query GIS. Making maps alone does not justify the high cost of building a GIS. The same maps may be produced using a simpler cartographic package. Likewise, if the purpose is to generate a tabular output, then a simpler database management system can work. Any statistical package can work. Why GIS? So it's a spatial analysis that requires the logical connections between attribute data and a map features, and the operational procedures built on the spatial relationships among map features, and that's something so important. And these capabilities make GIS a much more powerful and cost-effective tool than automated cartographic packages. So that's the reason, you may find that it's not an AutoCAD is different and a GIS package is different. Database management system is certainly very different than GIS. We need to understand the relevance of the functions. We need to understand even the other cartographic packages or the database management systems, which are generally just one step less than or below GIS. So now let's talk about using GIS for spatial analysis. Spatial analysis in GIS involves three types of operations: attribute query, known as non-spatial, spatial query, and generation of new data set from the original database. Right? So these are the ones which are there. So in case, let's take a journey forward and understand about the GIS usage in spatial analysis. GIS can interrogate geographic features and retrieve associated attributes. Obviously, that's the reason why we are using GIS. Information called identification. It can generate new set of maps by query and analysis. It also evolves new information by spatial operations. Here are described some analytical procedures applied within GIS. GIS operational procedures and analytical tasks that are particularly useful for spatial analysis include: number one, single layer operation; number two, multi-layer operations; three, topological overlay; fourth, spatial modeling; fifth, geometric modeling; sixth, calculating the distance between geographic features, calculating area, length and perimeter, geometric buffers, point pattern analysis, network analysis, surface analysis, raster grid analysis, fuzzy spatial analysis, geostatistical tools for spatial analysis, so on. Single layer operations are procedures which overlay analysis is operation. That's something which is so very important. So overlay analysis is operation in GIS for superimposing the multiple layers of data set that represent the different themes together for analyzing or identifying. That means one layer over another layer. The sandwich that you eat, there's one bread piece and then you've got a cheese inside. Imagine a club sandwich and you have another bread piece and then you have a sauce, green sauce, then you have tomato there, another bread piece. Then you may have your potato slice there and then another piece, another color. So all these are layers and that's something is what is called an overlay analysis. Overlay analysis represent the composite map by the combinations of different attributes and geometry of data set or entity. Overlay is the operation of comparing variables among multiple coverages. And in the overlay analysis, new spatial data sets are created by merging data from two or more input data layers. Overlay analysis is one of the most common and powerful GIS techniques. It analyzes the multiple layer with common coordinate system and determine what is on the top layer. That means what we require is a common coordinate system, obviously. Overlay operations combine the data from same entity or different entities and create the new geometries and new unit of change. Overlay operations perform many types of analysis. For example, cropping pattern in the field, dominance of particular ethnic population in a region, age and sex composition of region, physical landforms of the surface, all those, Suppose I have to find the potential park size of population. So I'll create the map of density of population and the map of distance to parks of populated area. Then I'll superimpose both the layers and find the suitable location. Agree? It's also termed as a spatial overlay because it is accomplished by joining and viewing together separate data sets that share all a part of the same area. The result of the combination is a new data set that identifies the spatial relationships. Before the use of the computer, a similar effect was developed by the Ian McHugh and others by drawing maps of the same area of the same scale on clear plastic and actually layering them on top of each other. Map overlay is used in both model overlay of vector data and overlay of raster data. So what did I do? In that park experience, it was like the park, whatever is there, and then the distance, and they overlaid, and then you come to another third layer. So that's an overlay. Okay, remember your sandwich? That's an overlay. So there are 4 overlay operators in common use. Number 1, point in area, also known as point in polygon. Point in area, then you have line in area, also known as line in polygon. Area on area, also known as polygon and polygon, and weighted overlays. So now let's take a journey forward. Let's recapitulate. What are these 4 operators? Point in area, line in area on area, and polygon, weighted overlays. So now coming to these vector-based overlays, overlays of vector data combines point, line, and polygon features. In this data model operation rely on geometry and topology of the surface. Vector-based overlays time-consuming, complex, and computationally expensive. Please remember this. Vector-based overlays time-consuming, complex, and computationally expensive. For example, taking the ordering network layer of Ganga watershed and laying over it with the layer of the village, the result would be which order of stream of Ganga flow in which village. Let's talk about point in polygon operator. Point in polygon overlay operation will also generate combinative properties of point attributes of one layer and the polygon attribute of the analysis layer. It's a spatial operation in which one point coverage is overlaid with polygon coverage to determine which points falls within the polygon boundaries. After overlay operations, point assume that attribute of the polygon which they fall. It helps in formulating hypotheses about the spatial relationships between the occurrence of points and the attribute of the polygon. This kind of overlay operation can also be used to calculate number of points located in each of the polygon. So, for example, you want to find the number of temples which are there in that region. You want to find out the post offices. You want to find out the headquarter and all that, and you all would be able to find out that. Is it clear? But remember, all these layers are georeferenced, yes. Same cardinal points, lats and longs, and the scale also. Let's now talk about points in polygon, which we're talking about. So polygon on polygon overlay operations is another one. In the polygon on polygon overlay operation, I need to check before starting the input layer is should topological correct. If it is correct, output map will also correct. In the polygon overlay, it is essential to a new intersection and create polygon for new topology. The overlay of two layers of polygon will produce large number of polygons or increase the number of interaction zone. If the new polygon arcs and set of nodes have been shaped, then meaningful set of layers can be extracted. It's necessary to keep in mind that area should be common to both input features. For example, a farmer wants to know which part of field has loam soil for the cultivation of crops. The farmers will overlay the map of loam soil polygon on field polygon to extract a feature that meets both criteria, loam soil and in field, and in the cultivation of the crops. The variable it's produced by the farmer both are categorically or nominal data, and mathematician here developed a set of algorithm termed the Boolean operators for handling such type of information, and GIS analytics exploit the area on area overlay analysis, and Boolean operator is that base of polygon overlay which apply for vector data to discrete area object in this thing. But just remember, once we are doing that, all the maps should be the same scale, same projection, same scale, and that's very important. And of course, the same geo-reference too. So now we are learning about the operations. So now let's come to line in area overlay operations. Line in area overlay operations need to check, of course, the linear objects. And linear objects we recognize can be a road, can be a stream, and it should also be topologically correct. We all, of course, know it. Suppose I have to know about which road is going in forest area or non-forest. Simply, I need to overlay the line layer on polygon, and remaining extract layer will be result. I think we agree with this. Now let's talk about the point in area overlay operations, and of course which we've already done. So we have to all take care of all those basic elements and then overlay one over the other, and then we may find another third additional layer which is going to be a thematic layer which is going to give us a result. Now let's talk about another one that's called weighted overlay and the vector data model. The objective behind area on area overlay on a vector data model is to identify one or more parts of the new geometry that met simple criteria. Areas that did not meet the criteria were discarded, of course, and this was processed as a simple task or a single task. The function of weighted overlay is to determine a new set of values for the complete coverage based on a combination of input values. There are two tasks to perform that working with a vector data model. So, right, I mean, I hope you understand that we need to create weights. Some are just not important and some are important, and then we assign weights to that. So now, what are the two tasks? The two tasks are, one, to create a new set of geometries for the entire area, and to compute a new set of attributes for those of geometries. And after performing the above mentioned task is a matter of describing a mathematical equation to process the input values. In the first task requires you to extend the basic polygon overlay operations to consider every intersection between all polygons, and in every data layer, as you can imagine, this can be computationally demanding, especially if the GIS you are using computer topology on the fly and does not store it in the data structure. As we shall see, this is one of the reasons why weighted overlay is more frequently applied to a raster data model. But again, we all should remember that there are requirements for overlaying point, linear and polygon data in selected combinations. Example, points in polygon, line in polygon, polygon on polygon are the most common. The arcs of the input layer are split of their intersection with arcs of the union layer. Thus, the number of polygons in the output layer will be larger than the input layer. It is then the Boolean operation that uses this operation. Therefore, the output map corresponds to the area extend to the input layer on analysis layer or both. And union requires both the input and analytical layer of the polygon. And this operator is generally used for querying and analysis of the urban sprawl and other sprawls. Then we also have, so after union operator, we have intersect operator, which is so very clear in the figure 2 in the text. Intersect operator performs the intersection of two input layers, and the resultant layer will keep these partitions of the first input layer feature, which will fall within the second input layer region, and that is a feature that's common area of both the input layer. It uses the Boolean operator. And the point of caution is that the input layer may either be a point or line or polygon, but the analysis layer should be always be polygon, obviously, because we are getting all impressions on that, and that's something so very clear in the input coverage visual graphic that you're seeing, and the intersect output coverage that you're seeing in a graphic, and that's something so very important. So let it be line, let it be point or anything, but the moment we see it, we see ultimately the output is what? Polygon. Yes, because map is a polygon, map is an area which is having different point, if you remember your first lesson, second line and all that. So now let's talk about the polygon overlay. Polygon overlay is often used for site selection or suitability analysis. One problem with vector overlay is the possible generation of silver polygon, or we call it sliver polygons. And these sliver polygons arise from inconsistencies and inaccuracies in the digitized data, and which actually, just remember, it should actually be corrected. We all know that, and some important overlay operations of ArcInfo are discussed here. One of them is CLIP, CLIP, creates a new map that includes only those features of the input layer that falls within area extent of the CLIP map. The input layer may be point, line and polygon, but the analysis layer, CLIP layer, must be polygon layer, and this operator is used to extract a smaller data set from the larger data set. For example, in the extraction of the city from the city map, and the city boundary is considered as the analysis layer, as so very clear in the graphic. The input layer is there, and the analysis layer is there, and the output layer is there, and we can see the clips. The next is erase, E-R-A-S-C, erase. Erase is a reverse process of clip, where the features of the input layer that fall within the boundary of the analysis are erased, and those fall outside the boundary of the analysis layers are retained. And the retained layer will have all attributes from the input layer only. The input layer may be point, line and polygon, but the analysis layer is always going to be, guess, yes, polygon. And we can see so clearly in the diagram. Next is split, S-P-L-I-T. It divides the input coverage into two or more coverages. For this, a series of clip operation is performed, and each resultant layer contains only those portions of the input layer that are overlapped by the polygon satisfying the specified criteria. For example, a national forest cover can use split to divide vegetation cover by district, so that each district can have its own vegetation coverage, and so very clear in the diagram, the logical operator, where you can see the spatial result and you can see the tabular result. Now let's come to update and identity. Update uses a cut and paste operation to replace the input coverage and the map feature. So it's a logical operator, right? And we can see in the graphic the spatial result and the tabular result. The input layer will be updated. Updated means it can be replaced by the analysis layer for generating the output layer. It means the resultant layer will have features from the input layer in the non-overlapping region and the feature from the analysis layer for the overlapping region. Both the input and analysis layer have polygon topology. And this operation is useful for updating the existing coverage with new map features and in limited areas of coverage. For example, we have the land use map of 1990 and the build-up area map of 2000. And the map of 1990 will be used as the input layer, and the map of 2000 can be used as the analysis layer to get the updated result. And the result layer will generate the urban sprawl, and it serves the user for digitizing the coverage. And now in case if we have a data of the 2010 data and the 2017 data, we can again further redo the same performance, and we can do it. Next operation is identity. So identity operation is where you get overlays, polygons, and keep all these input layer features and only those features from the analysis layer that overlap the input layer. So what we understand is the resultant layer will have the same spatial features as that of the input layer, and in case of the polygon overlays, the number of polygons in the output layer will always be, tell me, make a guess, larger or smaller? Of course be larger in number than the input layer. So what we have is a line and polygon graphic which you can see is, and the polygon graphic. So this is what you know. so very clear and so very visualized. We can do it in the graphic which we are seeing. And all this is expressed in Boolean operation. And Boolean operation is an input map and overlay map, or is an input map. The input map may contain point, line or polygon. The words of caution is that the operation can only be ideally applied if the map boundary is precisely maintained. Besides these operators, a number of other operators are also there. You've got merge, you've got append, you've got eliminate, reselect, dissolve, etc. are also used in the vector overlay operation. Okay, so just remember that. Then we have the raster based overlay. Overlay of raster data set is again raster, you remember? You remember from your earlier lesson, what is raster? Yes, raster is the one, all that in grid. It's an array of matrix arranged in lines and rows and columns. Yes, now we're talking about the grid based analysis. Till now we were talking about the vector based analysis. So now let's set our mind on raster based overlays. Overlays of raster data set combine pixel based calculations or map algebra. It is quick, straightforward and efficient data set for operations. It is known as cell by cell combination or operation. It is computationally less demanding. Overlay in raster data set include 2 or more different sets of data that derive from the common grid, and each separate set of data are usually specified numerical value. In the raster, these values are mathematically merged together to create a new set of values for a single output layer, right? And the raster based overlay is done for creating, say, risk services, sustainability assessment, values assessment and other procedures. For example, raster based overlay divides the habitat of an endangered species into a grid, imagine, and then getting data for multiple factors that have an effect on the habitat, and then creating a risk surface to illustrate what sections of the habitat need protecting most. If 2 grids are aligned and have the same grid cell size, then it is relatively easy to perform. A new layer of values is produced from each pair of coincident cells. That means try that both the layers have same size of the grid, and that's so very important. That's called scalability. So that means in case if we have that, the value of those cells can be added, subtracted, divided or multiplied. The maximum value can be extracted, mean values calculated, logical expression computed and so on. And the output cell simply takes on a value equal to the result of the calculation. So if it's addition, the output value would be like that. If it's minus, then it's like that, multiplication, so on and so forth. So I think it's clear? Yes. Most sophisticated spatial modeling is undertaken within the raster domain, and each point can be addressed by a part of a neighborhood of surrounding values. If all the neighboring points have the same attribute value or they grouped together, is termed as region. Raster map overlay introduces the idea of map algebra. It means in the raster data processing, some analysis uses individual cells only and some rely on the neighboring. So you need individual cells or the neighboring and the regional associations of the cells around it. Thus, the raster data processing methods can be classified into the following categories. Number 1, local operations. Number 2, neighborhood operations. And number 3, regional operations. So, you've got a local operations, neighborhood operations and regional operations. Local operations are based on point by point or cell by cell analysis. The most important of this group is the overlay analysis. In the raster based analysis, either the logical or arithmetic operators are used. Logical overlay methods use operators AND, OR or XOR. That means exclusively OR. XOR, AND, AND, OR, OR and XOR. XOR is exclusively OR. Mathematically AND multiplies the individual cells, whereas logical OR and XOR add individual values of the corresponding cells. The most important consideration in raster overlay is the appropriate coding of the features in the input layer. What is important? Appropriate coding of the features in the input layer. The raster overlay is affected by the resolution. What is the resolution of the cell? And scale of measurement. Scales we all know. What are the different types of cell? Nominal, ordinal, interval or ratio? Yes, that's something which is there. It is advised that the resolution and the scale of the measurement of both the input and analysis should be compatible. Basic arithmetic operators in raster overlay operations are addition, subtraction, division and multiplication. Simple maths. All these operators are explained there with the self-explanatory diagrams which are so very clear in the adjacent graphic. To begin with, let us look at the graphic which is there of the subtraction. 10 minus 3 is 7. Yeah, it's based on same basic maths. Yes, I'm very happy that you've learned that. And each operation would be performed cell by cell. And the cell by cell operations are termed as location specific overlay. But assigning values to the entire thematic region create a new layer and termed as category wide overlay, right? This is a category wide overlay. So then we have local neighborhood operations, and these are also known as focal operations. And it uses the topological relationships of adjacency between cells in the input raster layer to create a new layer. And this operation assumes that the value of particular cell is affected by the value of the neighboring cells. Hence, a moving window of 3 into 3 cells is generally applied on the input raster layer. And the value of the output cell may be either the average of all the cells of the moving window, or the central cell of the windows, or the median cell of the window. And that's so very important. Then we have operators on regions that we call regional operators. They are also known as zonal operations. Region is a zone, agree? It may just not be a next neighbor, it will be a combination of a neighbor. Region, yes, very good. Generally, a region is defined as the area with homogeneous characteristics. In raster model, it has been defined as the collection of cells that exhibit that same attribute characteristics. Though it also uses two input layer, but the mode of operation and the purpose is altogether different from the local operations, as it uses the boundary of one raster layer to extract the cell value from the other raster layer. The major purpose of this kind of operation is to obtain relevant data from the existing layer for further spatial analysis. There is no uncertainty in the location of the region boundaries because they are in the perfect registration. So remember, registration is so very important, otherwise it's very difficult. Okay? So now let's come to the next operation. It's called reclassification or a method. Reclassification is method of changing the attribute value without altering the geometry of the map. In fact, it is a database simplification process that aims of reducing the number of categories of attribute data layer. Accordingly, features adjacent to one another that have a common value will be treated and appear as one class. Reclassification is an attribute generalization technique. Typically, this function makes use of polygon patterning techniques such as cross-hatching and or color shading for graphic representation. It usually uses either logical or arithmetical operators for raster data or arithmetical operator for vector data. After reclassification, the common boundaries between polygons with identical attribute values are dissolved. Consequently, the topology will be rebuilt. In a vector-based GIS, boundaries between polygons of common reclass values are dissolved to create a homogeneous map. And the dissolved map boundaries based on specific attributes value often result in a new data layer being created, agree? Almost all GIS software provide the capability to easily dissolve the boundaries based on the results of a reclassification. Some systems allow the user to create a new data layer for the reclassification, while the others simply dissolve this boundary during data output. The exact process of the undertaking a reclassification varies greatly from GIS to GIS. Some will store result of the query in query sets independent from the DBMAS, while others store the result in a newly created attribute in the database management system. So I think by now it is clear what is overlay, and we've understood different operators, we have understood different use. Let's now get going and understand the application of overlay operations before we wind up this lesson. Let's talk about a suitability model, and this can be used to find the best location to construct a new school, hospital or police station, industrial corridor, etc. Certainly land uses are more conducive than others for building a new school. For example, forest and agriculture were more favorable than residential housing in this model. It was desired to locate the school on flat slopes, near recreation sites and far from existing schools. For this site suitability, overlay keeps in mind some points. Selection of the criteria is important. We need to reclassify the data as per the criteria. We need to overlay Boolean or map algebra. We need to extraction and representation of the suitable sites and all that. For example, and so that's something which is so very important. So that means after, in case if we have input all this data in a correct way, in a correct scale, we can then find out that which is the best suitable site for a school based on the input data. Okay? So now after selecting the best possible site for school, say now we want to find a location for the nuclear waste repository. So for this site should be an area of suitable geology site, must not be easily accessible, must be away from high population, and site must be outside the area of conservation in case nuclear waste repository we want to find out. So we need to create layers from that. So now let's just talk about another example, say a vector overlay operation. An example says the urban infrastructure. We need for minimum layers for overlay analysis, how GIS is happening in the infrastructure world. If you're wondering about the application shaping the infrastructure, of course, what is happening is that there's lot many overlay analysis can be done, because today for urban infrastructure if you're talking about, we are basically considering or remodeling the world. Urban development and the planning can be implemented more efficiently with the help of the GIS, we all totally agree by now. And the few factors which we consider or choosing the location for urban establishments are generally, number 1, land should be vacant, number 2, accessibility to water resources, number 3, area of vacant land, number 4, the vegetation, how's it, the demographic composition. So that means for everything we need a layer, we need to create a problem. We need to visualize the layers and then we start working on it. As it becomes super simple to analyze the above factors for GIS tools like Hexagon and so on, we can find out the most suitable site for the urban infrastructure, right? Another example can be, say we want to have the underground water utilities. Of course, for this the pipeline network can be better planned with the GIS data as it allows better visualization and enhanced active management. Available water resources, assets, networks, pipelines can be stimulated with accuracy to GIS maps. But that's something which is so very important. That means we again need to visualize all those layers which are there, all the directions which are there, and we can further find out this. The third, in case if we want to create maps or we want to visualize the spatial data for water management. The main task of water management are deciding the distribution mechanism, collection of the drainage storm water management and so on. So they create layers. Then another, so all these examples you can think of, let's say the metro system which is going on. So in making metro ecosystem perfect, we need to have now for this real-time data. Promoting and facilitating the excellent access to geospatial data, the metro ecosystem is one of the best applications of GIS. Sharing the accurate data in real time, planning the metro station and analyzing the moving trains is made easy now once we know it's through GIS, and that's something which is happening. So today we are having lot many data which is there. Technology is still growing and excelling. And another example, so that means I can go on and on with the example. Let's now go with a recent example of this earthquake in Mexico. This earthquake in Mexico was at 7.1 Richter scale magnitude. It caused a lot of destructions, huge loss of life and property. The death toll in this tragedy has crossed 225 and thousands more were injured, missing or lying in the debris waiting to be rescued. Epicenter of this powerful quake was in Puebla, which is about 80 miles from Mexico City. So then this, consequent of this overlays, because we had the map before, Esri had created a map of impact, mapping the impact, and this is with all the layers. and created a summary map so as to entirely focus on the region and provide accurate and detailed analysis, highlighting the region most affected by the earthquake. SRE has developed this enhanced shake-up map that shows the impact of the devastation quake on nearby population. It could only happen because of overlay analysis. An impact summary map is used mostly in situations of the emergency to gauge the impact on the ground and very quickly communicate this to anyone interested in knowing about. It is very helpful in giving the crux of the matter to the people and contribute to the dissemination of information that would be essential in rescue operations and evacuation of people trapped in disaster, right? So out here, you found that, in this map, in case you look at the visible graphic, different colors for different figures were there. In the map, there are 4 colors, orange representing 447K total population and 114K households, yellow denoting 10.2 total population and 2.6 total households. Then you had green and blue representing again 8.7 million and 4.3 million people respectively, along with 4.3 million, 10.8 million households. MMI scale with 4 color bands, the tool played a very important role, and enriched layer tools were also provided. So what we basically I'm trying to impress upon you is that you need to visualize layers. And though in this SRE has also evolved the enriched layer tool. So in case if you feel that this layer or this data is much more important, then you can create a library for it, and then that data can be even added in the real time, and then the new overlays can be created to analyze the data of the number of people residing in localities near a library, so on and so forth. Similarly, if a corporation wants to build a retirement community center, it can avail a tool for demographic composition of all the neighborhood in the vicinity. We can use enriched layer tool to use high quality data that is fetched from many resources and is regularly updated. And that's something what we're calling crowdsourcing, and so we're creating a new type of layers. So that completes my chapter today. So what all we have learned today? We have learned that GIS is a great decision making tool in problem solving environment. Number 1. Number 2, spatial analysis is a vital part of GIS and can be used for many applications like suitability, natural resource monitoring, environmental disaster management, and many more. Another thing we've learned is that the vector and the raster based analysis functions and arithmetical, logical and conditional preparations are used based on the recovered derivations. The most important thing which we have learned is visualize layers, visualize themes, remember your objective, and go ahead and perform overlay analysis. I hope you're going to do that, and I hope you have understood from this lesson. Thank you very much. Thank you and God bless.